Well, welcome back, ladies and gentlemen, and we are talking about thermodynamics and talking about Gibbs free energy, right? And just to give us a little review about Gibbs free energy, we say, hey, Gibbs free energy lets us know something about spontaneity, right? That when my Gibbs free energy is less than zero, my process, my forward reaction, my process is thermodynamically favored, or like I prefer to say, it's spontaneous, right? And if my spontaneous in the forward direction. Good. And if my delta G is greater than zero, that means I am spontaneous in the reverse direction. And if my delta G equals zero, then I am at equilibrium, right? Good. And then we also say, well, what is this delta G thing? And I said there are two ways that you can calculate it. You can use tables if you are at standard conditions being 298 K in 1 atmosphere, or we could calculate delta G at standard conditions using, this is using the tables here, right? Or I can use my delta H tables and my delta S tables, and that will also calculate a delta G for me. And then last time we were talking about what if I am not at standard conditions. So at non-standard temp, what did we say? Well, we said that delta H and delta S are not significantly affected by temp. So what was our equation for non-standard? Well, we're going to say that our delta G at any temp is equal to, since my delta H is not significantly affected, we're going to say delta H prime minus T delta S prime, where this T is the real T, not 298, the real temp. Good. So that's what we said for non-standard temp. What about non-standard pressure? Okay, now we got a problem with delta G at non-standard pressure. Here's why. Delta S is affected significantly by pressure, and we need to use a conversion for that. My delta S at any pressure is going to be equal to my delta S at my standard conditions minus R log of Q. Now, what are my R's? First of all, my R is my ideal gas constant, but it is in a more favorable unit, right? It's going to be 8.314 joules per mole Kelvin, or depending if this makes it easier to calculate, 8.314 times 10 to the minus third kilojoules per mole Kelvin, and that will come in handy soon. And what is our Q? Well, our Q is our, that's a nice arrow, isn't it? Reaction quotient. And what is that? Hey, remember we said that I had a KEQ, and it is concentrations, or let's go with KP. We have a KP, and I have a pressure over a pressure times a pressure. And I said I have a Q, which is equal to that pressure over pressure over pressure. These are all equilibrium values. These are non-equilibrium values. Well, that's the Q we're talking about. We're talking about the Q that is the same expression as your K, except for you're at non-equilibrium conditions. So that's a way we can do that. That's our correction for S. So when we kind of, let's walk through. We'll start up here with this and then see what we get, okay? So we have our delta G equals delta H minus T delta S, right? We said that, hey, my delta H is about the same, so I have delta G is equal to delta H prime, those are about equal, minus T. Now let's substitute for my delta S that we looked at right here. Let's substitute this in. And what do we get? We get delta S prime minus r log of q, minus r natural log of q. Okay, so this is a wonderful equation. This will work all the time. But you can simplify this a little bit. Let's go ahead and multiply through with my t. So my delta g is equal to delta h prime minus, now I multiply through by my t's. So I get t delta s prime minus rt natural log of q, right? Looks good to me. And now I'm going to multiply through by my -1, all right? So delta G is equal to delta H minus T delta S plus RT natural log of Q, right? I just multiplied my negatives through. Now, if you're really sharp, what do you see here? What is delta H minus T delta S? Well, that is what? That's my delta G prime. So I have delta G equals delta G prime plus RT natural log of Q. And there you go. This is for G at any pressure. Got it? Delta G at any pressure is equal to delta G prime plus RT natural log of Q. So let's do a problem. You ready? Here we go. All right, so let's do this problem right here. I'm going to probably need a little bit more spam, maybe not. Okay, so what do we want to get? We say that my delta G equals delta G prime plus RT natural log of Q. So first, what would my Kp be? If I wrote my Kp would be the pressure of my ammonia squared over the pressure of my nitrogen times the pressure of my hydrogen cubed. So what's my Q? Well, it's the same thing, except for it's just not at equilibrium conditions. So that would be my Q. What's my delta G? Okay, my delta G prime, excuse me. Delta G prime would be equal to delta G, 2 times my delta G, a formation of my NH3, minus delta H of my delta G of my formation of N2, minus 3 times delta G, a formation of my H2O, H2. So when I look up in my table, I look at my wonderful values, and what do I get? How about a -16? I have 2 times -16.66 minus 0 minus 0. So that looks to me like that is a -33.32, -33.32, and we want to be very careful here. Kilojoules per mole. Got it? All right, I think now I can start putting everything into my equation. So here we go. Delta G is equal to my delta G prime, -33.32 kilojoules per mole, plus R, that means I'm going to need kilojoules per mole, 8.314 times 10 to the -3rd. T, what's my T? Well, my T is 298, and this is what? Kilojoules per mole Kelvin, times 298 Kelvin, times my Q, natural log of my Q. And what is that? 0.5 squared over 1 times 3 cubed. Got it? So let's run our numbers. Let's see if we can get the right answer. So I'm going to work from my Q backwards. 0.5 squared divided by 1 divided by 27, which is 3 cubed. Take the natural log of that. Get a -4.68 times 298 times 3. Nope. Times 8.314 times 10 to the -3rd. good, which is a minus 11.6 plus 33.32 negative plus a negative 33.32, and I get an answer of negative 44.92 kilojoules per mole. There you go. You guys try the next one, and I'll bring you back. Or bring me back when you're ready. Okay, I think you can handle this. The beautiful thing here is what? It's the same reaction, so my Q prime is going to be the same number. So my delta, not Q prime, delta G prime. So my delta G is equal to negative 33.32 kilojoules per mole plus R, 8.314 times 10 to the minus third kilojoules per mole Kelvin times the temp. Still better be 298. Yes, indeed. Still 298 K, right? Times natural log of my Q. So this time, what's my ammonia? 2.0 is my ammonia pressure. So that is squared over what is my nitrogen pressure? 0.5 times my hydrogen pressure, 0.75 cubed. Okay, let's run the numbers and let us hope we are right. 2 squared, which is 4, divided by 0.5, which is 8, divided by 0.75 cubed, and I get like 18.96. I want to take the natural log of that. Good, and that gives me 2.9 times 298 times 8.314 times 10 to the minus third. And that gives me a positive 7.29 plus 33.32 negative, and I get a negative 26.3 kilojoules per mole. Woohoo! There you go. So you've just handled non-standard temperature. Non-standard pressure. Great. La. Is that right? Do I want to go there? Yeah, I think so. Okay, so now we want to take a look at this one. What is the equilibrium? Oh my gosh, equilibrium K for this reaction. Well, what do we remember? Let's go back to our notes for a second. And let's go back up here. Yoink, yoink. What did I say at equilibrium? Whoops. At equilibrium, my delta G is equal to 0. So can we use that? Sure we can. Let us come down here. And now what do we know? My delta G is 0. So let's talk about finding K, and this is a KP at non-standard pressure. We're going to use this, start off with this equation, delta G equals delta G prime plus RT natural log of Q, right? And we're going to say delta G equals 0 at equilibrium. And Q equals what at equilibrium? Q equals my KP. There we go. So that means I have 0 equals delta G prime plus RT natural log, not of K, not of Q, but of KP. So let's do some rearranging. So what do I get? I get over here a negative delta G prime is equal to RT natural log of KP, which means I have a negative G prime over RT equals the natural log of KP. How do I get rid of that natural log? Take an E of both sides. So that means KP is equal to E to the negative delta G prime over RT. There you go. And once again, watch your units. This is going to typically be in kilojoules per mole. R is going to need to be in kilojoules per mole Kelvin, and my T is going to have to be in Kelvin, right? I better write Kelvin so we don't confuse Kelvin with K. Good. So let's go do one. Yoink, yoink, yoink. Oops, too far. Yeah, there we go. All right. So we need our, what did we say? E equals negative delta G prime over RT, not E, Kp equals e to the negative delta G over RT. For this equation, fortunately, we've already calculated our delta G prime, right, from the previous problem, and it was a negative 33.32 kilojoules per mole. Great. So what's my Kp equal to? It's going to be equal to A, talking German, E, to the negative, be careful here, negative 33.32 kilojoules per mole over R, 8.314 times 10 to the minus third kilojoules per mole Kelvin times 298 Kelvin. Great. And if we're lucky, we will get a number. Let's find out what it is. 33.32 negative divided by 8.314 times 10 to the minus third divided by 298, negative 13.44, but we have to take the negative of that value. So that is really a e to the 13.44. And so when I take the e to the 13.44, I get a 6.9 times 10 to the 1, 2, 3, 4, 5. And that is my K. Great. You guys do the next one. Bring me back when you're ready. Here you go. All right, when I looked at my values here, first of all, we're going to have to calculate a delta G prime, right? So my delta G prime is going to be equal to what? 2 times the delta G of formation of my HBr minus delta G of formation of my Br2 minus delta G of formation of my H2. And so that's going to be equal to what? Negative 53.22 times 2 minus 0 minus 0. So that's going to be equal to a negative 106.44 kilojoules per mole. Good. So my Kp equals e to the negative delta G prime over RT. So that's equal to e to the negative 106.44 kilojoules per mole over 8.314 times 10 to the minus third kilojoules per mole Kelvin times my 298. Great. Doink, doink. Let's run the numbers. Let's hope we are right. 106.44 negative, and then I take the negative of that, so that means it's positive, divided by 8.314 times 10 to the minus third, divided by 298. It gives me like a 42, is that right? I'm going to take my e to the x, and I get 4.5 times 10 to the 18th. So that is what my K would be. Great. One more concept, and then we're done. Woohoo! All right, what's the equilibrium pressure of my CO? Okay, this is kind of an interesting question, isn't it? I look at this, it's an equilibrium. I want to figure out my equilibrium pressure, and here's the cool thing. I have a solid, I have a gas, right? Well, what would my K be? My Kp? Well, my Kp is equal to what? The partial pressure of CO2. So if I find my K, guess what I find? I find my equilibrium pressure of CO2. So really all they're asking for here, when they say find the equilibrium pressure of CO2, they're asking me to find the Kp. Now, we would think that's easy. We'd say, okay, yeah, we're just going to take what? Delta, we're going to take delta G is equal to delta G prime plus RT, the natural log of Kp, right? Except, what do you see there? That looks like an 1100 K, which is not equal to 290 K, which means I cannot calculate a delta G prime. So I have to go back to how do I calculate delta G for non-standard conditions. And you guys remember that? non-standard temp. I'm going to have to say that my delta G at any temp, in this case at 1,100, is equal to my delta H. My delta H prime. And I just had a blowout of a pen. Delta H prime. Delta H prime minus T delta S prime. So I'm going to have to fit that in. So what would that mean? My delta G equals delta H prime minus T delta S prime plus RT natural log of Q, right? This should be Q at this time, right? Sorry about that. And then I'm going to say let my delta G equals 0 and my Q equals Kp at equilibrium. And so what do I get out of this? I get 0 equals my delta H prime minus T delta S prime plus RT natural log of Kp. And we do some algebra. Let's take these things over to the other side. And so I would get T delta S prime minus delta H prime over RT. All of that has to be to the E equals my Kp. You guys follow that? Maybe I did that too fast. Let's do it one step at a time so I don't confuse you. So T delta S prime minus delta H prime equals RT natural log of Kp, which means that T delta S prime minus delta H prime divided by RT equals the natural log of Kp, which means my Kp equals E to the negative T delta S prime minus delta H prime over RT. So that is how I can find my Kp at non-standard temp. All right, let's do it. Oops. There we go. Man, oh man, oh man, oh man, oh man. Okay, we just have to plug in some numbers. I have what? I need to find my delta H prime, which is going to be what? Delta H formation of my CO2 plus the delta H formation of my, what is that, BAO? BAO minus the delta H formation of my barium carbonate. And then I need to do the same thing for my delta S, which is equal to delta S of my, is my S prime of CO2 plus the S prime of BAO minus the S prime of my barium carbonate. Let's run some numbers. I happen to have those numbers here for me. So carbon dioxide is a negative 393.5, right? My barium oxide is a negative 553.5. My barium carbonate is a negative 12,163, right? And when I add all those together, I get a 269.3 kilojoules per mole. Good. On my S's, I get a 112.1, a 70 plus a 70.42 minus a, excuse me, that's not right here. This is a 213.6 for my CO2, isn't it? And then this is a minus 112.1, and that should equal, maybe I should check this to make sure I didn't make any mistakes. So 171.92. Here we go. Let's make sure. 213.6 minus 7 or plus 70. Wow. 213.6 plus 70.42 171.42 minus 112.1, and yes, 171.9. Now be careful, joules per mole Kelvin. All right, let's start plugging this stuff into this equation up here. My Kp equals E to the negative, what do I need? T, delta S. T is what? 1100 Kelvin. Delta S is what? 171.92 joules per mole Kelvin. But I need to convert those joules from joules to kilojoules. So 1 kilojoule per 1,000 joules, right? And then what do I have to do? I have to subtract my delta H. And what's my delta H? 269.3 kilojoules per mole. Great. And what else do I have to do? Divide by R. And I have to have my R in 8.314 times 10 to the minus 3 kilojoules per mole. And divide that by a T. And what's my T? 1100 K. Woo, mamma mia. All right. Let's see what kind of number we can get out of this. Got to be careful here. So I have 1100 times 171.92 divided by 1,000. Okay, that gives me like 189 minus 269.3. Okay, that gives me a minus 80 divided by 8.314 times 10 to the minus third divided by 1100. Okay, so that gives me an 8.768, but I have to take the negative of that. That is a negative, so I have to take the negative of that, and I get E to the 8.768. So I make that an E thing, and what do I get? I get a number of 6426. Uh-oh, I bet I made a mistake somewhere there. Let's try that again. Where did I mess up my calculation? Let's try it. That is not the right answer. Here we go. Let's run the numbers again. 1100 times 171.92 divided by 1,000. Okay. 171.92 divided by 1,000. Got it? Minus 269.3. And so that gives me an 80 when I take the negative of that. Divide that by 8.314 times 10 to the minus 3 divided by 1100. And then the E. Nope. Then I've made a mistake somewhere. What have I done wrong? Let me figure this out. I'll bring you back in a second. Oh, I caught it. It's right here in this equation. Holy moly. Where did I get that negative? I shouldn't have that negative, right? When we just look at the solving here, there is no negative. There's no shoot. Go back. I just killed that. Where's my pen that works? It's in my pocket. Good. There is no negative in here. I shouldn't have had that negative, right? There is no negative here. There's no negative there. So it's just Kp is equal to E to that value. Sorry, folks. And then come down here. So there's no negative there. Good. So this should be E. All my values are right except for that goofball number I was giving you. So 1100 times 171.92 divided by 1,000 minus 269.3. Great. Divide that by 8.314 times 10 to the minus third. Divide that by 1,100, and you get a negative, there we go, 8.68. And take the E of that, and you get 1.6 times 10 to the minus 1, 2, 3, 4 to the minus 4. That's my Kp, which also equals what? My equilibrium pressure of CO2. So that means my equilibrium pressure is 1.6 times 10 to the minus 4 atmospheres. Woohoo! That's it, folks. I hope you enjoyed thermodynamics.